Okay, so if you remember, we have been talking about digital transmission, right? Transmission of information in the form of pulses, right? And our reason for doing that was, we have discussed that a couple of lectures earlier, we are able to trade off bandwidth with performance against noise. We can really get very good performance if you do this, right? And our immediate concern was how to represent our analog information via a digital representation of the same. We discussed one simple method of doing that in the previous class, namely delta modulation, and its improved version, adaptive delta modulation. There are many variants of these delta modulations, and but the purpose is the same, to try to achieve a good representation of a basic information, analog information, into a sequence of binary pulses, right? Two level pulses. These two level pulses are typically having opposite polarity, positive and negative polarity. Now this is one way of doing things. Another way of representing or converting your analog information into digital form is through what is called pulse code modulation, which is essentially a quantization process followed by an encoding process, right? So we will discuss the pulse code modulation in the context of communication theory in today's class. So if you look at this second method of doing things, basically we have this block diagram for a pulse code modulator, and you will see where the name comes from in a few minutes. You start with your message signal as before, and the first thing you do is sample the message signal using sampling theorem, right? That is at a rate sufficient to, we are assuming of course that the message signal will have some band limitation, it will be within some bandwidth, and therefore it should be possible to sample it adequately by sampling at a suitable rate. If it has a bandwidth of B, you can sample it at either 2B samples or more per second, right? And that will be a good representation or adequate representation of the continuous signal empty, because of the fact that we can recover the message signal, continuous message signal, from the discrete samples. This is sent to a block or a device which we call a quantizer. Okay, I will describe the quantizer in a few minutes. And the quantizer output essentially carries out a mapping, some kind of an allocation, that if this particular sample value that has come out, it lies in a certain region in the amplitude range, right, a certain interval. Basically the amplitude of the signal is now mapped into certain intervals, and then depending on which interval it lies in, that is the output of the quantizer. It tells you which interval it lies in, right, and then you convert that information or encode that information into a binary form. So that is the encoder, and that in fact is the reason why we call it pulse code modulation. So it is this encoded pulses, these are typically binary in nature. This mapping of the level from the quantizer output to a binary code, which is the final output, is the job of the encoder, right? And this is transmitted in the form of a set of binary pulses. So the final output is a sequence of binary pulses. Right? That's the final output of the PCM and pulse code modulators. So this is the PCM output. Let me discuss the quantizer in a little more detail. So let us say this is your message waveform, right? What you are really doing is you are dividing your amplitude range that you could consider into intervals, right? And you are now saying, okay, you are sampling the signal at a certain rate. These are the sample values. Right? You look at each sample value. So let's say these are, I'll just give some numbers to these levels 0, 1, 2, 3, 4, 5, 6, 7. Right? Okay. So basically what you do is the following. Look at each sample value. Let's say at this time instant you have, this is a sample value, and you find that this lies between the level 4 and level 5, which I have drawn in this picture, right? And right in the middle of this level, these two levels, you have a corresponding quantized level, right? So any point, any sample that falls between this, the 4th and the 5th level, will be represented by an amplitude corresponding to this quantized level. So you are going to effectively once again do some kind of an approximation. You are not really sending the true sample value of the signal, you are sending a sample value which is close to the true value, close in the sense that it lies in a small interval around the quantized level, right. So basically the process of quantization creates an error, but you decide to live with this error, right. That is a essential important point to note about PCM, that there is an error, just like in delta modulation there was an error in the presentation. After all, ultimately you are reconstructing only a staircase approximation to the actual signal, right. Similarly in PCM you are going to create an approximation, you are going to create an error, and this issue is important. In both these cases we are actually introducing a kind of noise, both in delta modulation as well as in PCM. In the process of converting this information into digital form, a certain kind of noise is getting introduced, right. We call it quantization noise, right. So this is as distinct from the noise that is added by the channel, right. So you may well ask, what is the use? You are replacing one kind of noise with another kind of noise, right. The answer to that is, fortunately this kind of noise is under our control, right. We can reduce it to the level required by choosing the parameters of the modulator suitably, right, and channel noise is not really entirely in our control. So anyway, this is a quantized level. So this let's say this will be level number 5, right. So the quantizer output would produce a mapping which says that the level to which it is getting quantized is 5, right, and the encoder will produce a binary representation of the number 5 at its output, and that is the one which will be actually transmitted, right. That is basic idea of so you will be transmitting the number 5 in a binary form. You will use an appropriate number of bits to do that, right. So now it's important to appreciate that between one sample and the next sample you will have to transmit not just one pulse. Is it clear? Suppose you are transmitting the number 5. Suppose the total number of levels that you have, as I have shown here, is 8. Right? You have 8 possible levels here. So you will require a minimum of 3 bits to represent these 8 levels. Right? So, and I must use these 3 bits to represent just this sample value. So I need to send a sequence of 3 pulses with a particular 1-0 combination, right, to represent the sample value. So between one sample value and the next sample value I have to transmit 3 pulses, right. So therefore the pulse rate at which you will be making the transmission is much faster than, much larger than the sampling rate. Therefore the bandwidth requirement obviously will be high, right. So it has a cost in terms of bandwidth, which depends on number of quantization levels. Right. For example, if you have a larger number of quantization levels in a given interval, you will obviously have a better approximation of your signal by the quantization process, which will be nice, but the price that you will have to pay for that is, because you have a larger number of quantization levels, you require a larger number of bits to be transmitted between two successive samples, right, and the rate of transmission would therefore be correspondingly much higher, right. So, let us make a, if this is understood, can I proceed further with this? Let us look at the bandwidth issue. How much is the bandwidth requirement? Can we quantify it? Okay. To do that, to quantify this, let us denote by Q the number of quantization levels, right. I showed 8 quantization levels in the example that I drew in the figure a few minutes ago. In general, it will be much larger, because you want a good approximation of the signal, and approximation error to be rather small. Typically, for convenience, you will choose this Q to be a power of 2, so that you can represent it as an exact number of bits, every level to be in terms of a finite number of bits. So, typically it will be chosen to be a power of 2. So, 4, 8, 16, 32, etc., right, and therefore it will imply that you need to transmit n bits per sample. Is that clear? For every sample that you have, you will have to transmit n pulses, right. So, if your signal has a bandwidth of W, so message bandwidth M3, let us say is W, then your sampling rate 1 by Ts would be minimum of 2W, and the pulse rate, so that is your sampling rate, right. So, the rate at which you will have to transmit pulses, or the pulse transmission rate, will be equal to how much? 2NW, because for every sample you are transmitting n pulses. So, that is the number of pulses that you will have to transmit per second, right, and it is more or less common sense to electrical engineers that the bandwidth of that is required to transmit pulses will depend on the duration of the pulses, right. So, that means if you are transmitting 2NW pulses per second, what is the maximum duration you can have for each pulse? It is the maximum value you can have is 1 by 2NW, right, and the corresponding bandwidth will be proportional to the reciprocal of this duration, right. If the pulse duration is tau, you know that the spectrum of a pulse is the sync spectrum, right, and where is the first 0 crossings of the sync spectrum? Proportional to 1 by tau, right, minus 1 by tau to plus 1 by tau, right. So, roughly, of course, the actual bandwidth is a little larger, in fact it is infinite theoretically speaking, but even if you assume that most of the energy lies in a certain finite band, that will be proportional to 1 by tau, right. So, the actual bandwidth will be therefore some constant times 2NW, where this constant is appropriately chosen to say that okay, 99% of the energy of the signal lies in that band, right, but it will be proportional to 2NW. Is this okay? So, that is the typically this constant lies between 1 and 2, right. So, that is the required bandwidth, and as you increase the number of quantization levels, that will increase the number of value of n, and that will increase the required bandwidth, right. So, the pros and cons are you must use larger number of levels if you want a good approximation, and it is achieved at the cost of more use of more bandwidth, higher bandwidth. Any questions so far? Maybe we can just go one level further and write this relation as 2NW 2KW. This n is, you can also think of this n as log of q to the base 2, isn't it? N is log of q to the base 2. So, that is another way of writing the same result. The next thing we like to understand about this process is we have said that there is an error involved in the quantization process, right. So, we need to appreciate what, and therefore, this introduces a kind of noise right at the transmitter itself, whereas otherwise if you had transmitted the analog signal, that kind of thing is not happening, right. You are introducing some noise deliberately here, right. Of course, you have no choice if you want to do quantization. So, one of the important things to understand is what is the magnitude of this quantization error as a function of the number of quantization levels that you have. You like to quantify quantization error, which in turn will allow us to quantify the quantization noise. Sometimes it is also called quantization noise. Or let us calculate what is the signal to noise ratio that you can expect from a PCM system which uses a certain number of quantization levels, right. That is the analysis I like to briefly do. Introduce some notation for that. Let me denote by x the value of value of the message at any given sampling instant, right. Do not confuse this n with the n that I used a few minutes ago. This is the nth sampling instant. Denote by delta the quantization interval. We will assume that your signal amplitude varies between some fixed values, let us say from some value a to some value b, and you have divided that interval of values into q intervals, q subintervals, right. So, and the mapping is if x falls in the ith quantization interval, then what we do is we convert this x to a value x sub q. Go back to this picture. This is the actual value, but it will be converted to this level, which I am calling x sub q. This is, what is this value? This value is the middle value between the two intervals, typically m sub I. I will denote it by m sub I, right. So, m sub I is the midpoint of the ith interval, right, and therefore, you can say delta, the quantization interval, will be equal to b minus a, where b is the largest value, a is the smallest value, and you are dividing it to q subintervals. So, what is the value of the quantization interval? b minus a upon q. Well, b is the maximum value of x and a is the minimum value of x, and q is the number of intervals, right. So, this is some notation. Let me depict this in the form of a picture. Let us say you have this level x0, x1, x2. These are not the levels, these are intervals, right. So, I am calling this x0, x1, x2, x3, right, and the midpoints are represented by m1, m2, m3, and so on and so forth, right. So, we said that x sub q is equal to m sub I when x lies between xi minus 1 and xi, right. You are mapping the value of x to the value xq, which is equal to m sub I. The value of xq is equal to m sub I, where if x lies between the ith interval. The ith interval is defined as between xi minus 1 to xi. Is that okay? This is what I have been saying so far. Let me write an expression for x sub I. it will be equal to a plus the smallest value is a, right, which I am denoting as x0 here. A is nothing but x0. This is equal to a plus I delta, right, I going from 1 to 1 to q, or if you make it 0 to q minus 1, then it will be no. I think I am defining from x1 onwards, x0 being defined equal to a, it does not really matter, that is okay. And m sub I is the middle level of these two. So, it is xi minus 1 plus xi upon 2, right, that is the m sub I. So, with this notation we are ready to compute the quantization error. How will you define the quantization error? You had a sample value x, right. So, let me define what is quantization error. And you are converting this into a value x sub q. So, what is the error? X minus x sub q is the error, right. And average quantization error or average quantization noise power, I am denoting the error, thinking of the error as some kind of a noise, right, is basically the expected value of course, when we talk about error, error can be positive and negative. When we talk about power, we do not want to talk in terms of positive and negative values, we want to talk about the square value. So, essentially we are talking about the mean square value of the error, right. So, we take the expected value of x minus x cube whole square. That is the definition of average quantization noise or average mean square error that you have. So, this is a kind of mean square error, right. So, how will you compute this? X is average because x can take any values, x is we are taking x as a random variable, right, and in as much as x is a random variable, at different time instance or for different values of x you will see different values of the error depending on what you get, right. So, you have to take the average over the distribution function of x, right, and x lies between a and b with some probability density function, right. The domain of x is a to b, minimum value is a, largest value is b, right. So, you will take x minus x sub q whole square into the density function of x, which I am now denoting by small f sub x dx, fx dx, and that is the value of the mean square error. Everyone with me here so far? To proceed further, please note that this interval from a to b is composed of a set of sub intervals. So, I can carry out this integration over each of the sub intervals separately and add up all these, add up the sum, right. Instead of directly carrying out the integration from a to b, I can carry out the integration over this interval, then over this interval, then over this interval. It is the same thing, right. So, you can also represent it as sigma I going from 1 to q integral. So, the ith integral is from xi minus 1 to x sub I, and when you are considering x to lie between this region, what is the corresponding value of x sub q? M sub I, isn't it? Whole square fx dx. Okay. Any questions on this? So, let me denote this quantity by n sub q. This is the average noise, quantization noise that you have introduced. Okay? All right. Similarly, I can define an average signal power that you will see, right. So, the signal power at the quantizer output. Would be expected value of the quantizer produces the value xq, right? So expected value of xq square, and what is this equal to? In the same way as we did for the case of noise, basically we have just to take the integral of xq square fx x dx, right, which again you can split it into these q integrals. This is from a to b. In the qth interval, what is the value of xq? M sub I. So m sub I square, and this, because this is a constant in that interval, I have taken it outside the integral, and this will be x sub I minus 1 to x sub I of fx x. Right? So these are the two expressions you have, 1 and 2. This gives you the average signal power, this gives you the average noise power, and the ratio of these two will give you a measure of the fidelity of the quantizer output to the original signal which you are quantizing, right. So S sub q upon n sub q is a measure of fidelity or accuracy of your quantizer. Everything okay so far? Yes. This one?
Yes.
Just like in the same way, you are taking the average value of the quantizer output, so xq square, then
How do we separate the summation?
so all I am saying is the integral from a to b could be broken up into integral from x0 to x1, then x1 to x2, then x2 to x3. That's all I am doing, and summing them all up. So this mi square is actually part of this integral, but since it is independent of x in this interval, I have taken it outside the integral. Just like here I cannot take it out because it depends on x.
So would it be
Please speak out the doubt if you still have the doubt.
that's expression.
It's okay. Sure. All right. Now, to proceed further, this unfortunately is not in a form which will make any sense to us, right? It's too analytical. It's I mean, it simply doesn't give us a physical picture. To get a physical picture, we have to assume a certain distribution for the signal samples, right? Because unless we have a specific distribution, I can't simplify these expressions any further, right? And to keep the picture simple, let's keep this distribution, assume this distribution to be one of the simplest distributions you can have, uniform, right? X can lie between A and B, and let's say X can lie between A and B with a uniform distribution, right? That's the simplest picture that you can construct. So let's take an example, and that will give us a better picture. So let's assume that, let's say A is minus A, the lowest limit is minus H and the upper limit is plus A. So I am assuming the signal to lie between minus A and plus A, and uniform distribution of 1 by 2A. So I have taken the lower limit as some value minus A and the upper limit as plus A. Just again for simplicity. So then your n sub q, please note that in this case you can write your m sub I, the ith quantization level, to be minus A plus I delta plus minus delta by 2, isn't it? Let me rewrite it. Made a mistake here. M sub I is minus A plus I delta. Minus A plus I delta will take you to the next boundary, and the middle level will be delta by 2 lower. So that's, we can write this. So M sub I can also be written like this. I will substitute for this M sub I in the expression for n sub q. Is this okay? So let us now look at the expression for n sub q, which was summation I going from 1 to q integral x sub I minus 1 to x sub I into x minus m sub I whole square, and this one fxx is now 1 by 2a dx. Further is to I substitute for m sub I from here. So this is x plus a minus I delta plus delta by 2 whole square into 1 by 2a into dx. Alright. Now this is very easy. I mean, it looks cumbersome because of this constant, but if you were to do this integration, which is a very straightforward integration, and simplify this integral, basically carry out the evaluation of this integral, I will skip that step if you permit me. You can see that n sub q becomes I is equal to 1 to q 1 by 2a, that basically comes out, this comes out outside the integral, and the rest of the integral turns out to be simply delta cube upon 12. Okay. Can I skip that? Can you just evaluate this and in this boundary? Very straightforward to do that. So this becomes delta q by 12, and therefore since this is independent of I, you can write this as q times delta cube upon 12 into 2a, right? Because basically you have q similar terms, so you simply multiply by q. But what is the value of q delta? Q times delta is the 2a, the total interval in which the signal lies, right? The dynamic range of the signal in some sense. So this is 2a. So you are left with delta square upon 12, because q delta is equal to 2a. So very simple, neat expression you get for the noise quantization noise power. And as you can see, the smaller your quantization interval, the smaller the power in the noise process, which was intuitively expected, right? Similarly, if you were to compute S sub q, which is much simpler, of course, because that simply in this case, all of this integral of, maybe I should write, okay, I think it's obvious. Let me just go through that expression. This is 1 by 2a, right? So what is the value of this integral between xi minus 1 to xi, which has a width of delta? Delta by 2a, right? So that's the answer. In this case, of course, there is supposed to be an index, it seems to depend on mi, but again it's very simple to check that if you were to substitute for this mi and evaluate the summation, it turns out to have a simple nice closed form, q square minus 1 upon 12 into delta square. Essentially same delta square by 12 into q square minus 1. This essentially comes from the summation of this mi square. Substitute for mi as I given to you, and you can check it out. Again leaving that out for reasons of time, and it's something which is straightforward for you to evaluate. And that brings us to the value of S sub q upon n sub q to be given by q square minus 1. Very simple. This upon this, right? Or you can say approximately equal to q square if q is large, right? And q is much greater than 1. So that's the rule of thumb that you should use for finding out what is the kind of signal to noise quantization noise ratio that you can expect from your PCM quantizer. Of course, remember that there are certain assumptions you have made in deriving this expression. The most important assumption you made is that the samples have a uniform distribution between minus a and plus a, or a to b, right. So, with that assumption, this is the answer, which is useful from a rule of thumb point of view, but not very accurate for all kinds of signals. If you express it in dBs, the rule of thumb becomes something like this. This is in dBs. This will become 20 log q, isn't it? So, let us say you double your value of q. What is the number of what is the value of the improvement in the signal to noise ratio you will get? How many dBs? 6 dBs. 6 dBs? 20 log 2, right? So, for every doubling of q, you will get a 6 dB improvement in SNR. And doubling means what? In terms of number of bits? 1 more bit, right? So, you get a 6 dB improvement for every additional bit that you introduce in the representation. Right. So, that is a general rule of thumb. So, if you want something like 40 or 50 dB SNR, let us say 40 dB SNR, you must use at least 7 bits, rule of thumb, right. Typically use 7 to 8 bits in typical applications. 7 to 8 bits means number of quantization levels is between 128 and 256. So, either 128 or 256 or larger. The RMS value of the error, if you are interested more in terms of RMS value of error rather than signal to noise ratio, would be simply delta upon root 12, because it is delta, the noise power is delta square by 12. So, RMS error value is delta by root. Any questions so far? Now, this picture is good as long as this, the example that I took was somehow matched to the kind of quantization that I did, right. Let me elaborate what I mean by that. I took a uniform distribution, that means signal has equal probability of being there in any of the intervals that you, and these intervals are uniformly spaced, right. But suppose this the probability of the signal being in, let us say, one of this one interval is very different from the probability of the signal lying in some other interval, right. It can happen. The small values of signals, let us say, sometimes are much more likely than larger values of the signal, right. Then this kind of quantization that we have discussed is not a very good idea to use. This kind of quantization that we discussed is called uniform quantization, right. So, what we have discussed so far is uniform quantization. Uniform quantization is quite okay if your signal samples are uniformly distributed, right. So, they are okay for the uniform distribution that we discussed. But more likely your samples are not going to be uniformly distributed. They may have a Gaussian distribution. Actually, speech signals have a very different kind of distribution. They have Laplacian kind of distribution, right, very different kind of distributions. So, in that case, you can intuitively expect that a uniform quantization process is not the best thing to do, right. It is probably better to just take an example. Suppose X is Gaussian, right. That means the samples are distributed according to this bell shaped distribution curve, right, probability density curve. Now, in this picture, it is clear that the smaller values of the x are much more likely than larger values of x. right. X lying in interval here has this kind of probability. X lying in interval here has a very large probability, right. So, if you are going to use your number of bits for representation efficiently, I should crowd the quantization intervals in this neighborhood and space out them sparsely for larger values of x, rather than keeping all the quantization intervals of uniform size. Is that clear? Because then, although whenever I use a larger quantization interval, the error is going to be large, but fortunately that error will occur with much lower probability. So, the contribution of that to the average value of noise power would be much smaller. So, that is a reasonable thing to do. So, whenever you have a thing like this, you do not use uniform quantization, you use what is called non-uniform quantization. And non-uniform quantization will typically improve the effective value of S sub q by n sub q for a given number of bits or a given value of n, right. And the job is basically to find out how you should, I am sorry, I have not drawn a good picture, how you should distribute this interval boundaries and the interval and the quantization intervals, right. How you should space this value of x0, x1, x2, x3, x4, etc., and what should be the corresponding. Also, it's clear that I should not now use the middle of these two for my quantization level. Probably I'll use something which is biased towards the region where the signal samples are more likely to be located. So, instead of being on this side, it's slightly on the slightly to the right of the middle here, right. So, this will be M1, M2, etc., right. So, but this is a difficult problem, finding out the set of xi's and m sub i's, so that you get the best possible signal to noise ratio, right. That's the job of designing a non-uniform quantizer. That's one way of designing a non-uniform quantizer. Take into account the distribution function that you have, and using that knowledge of the distribution function, find out the best pair of values of x sub I and m sub I for all values of phi, so as to produce the smallest value of error, right, mean square error. So, that is a good interesting problem which has been solved in the literature, but rather difficult and involved. And because of the difficulty that is associated with this approach, there is a simpler approach to carrying out non-uniform quantization, right. And the simpler approach is the one which is actually widely used in practice, which I like to discuss. So, in practice, non-uniform quantization is achieved via what is called sample compression followed by quantization. So, followed by uniform quantization. Let me explain what I mean. Let us say you have this signal which has a non-uniform distribution. So, what I will do is I will pass the signal sample values through a nonlinear amplifier, right. The signal values are denoted by x, and the nonlinear amplifier outputs are being denoted by y, right. It is not a linear amplifier, it does not produce y equal to k times x. It's a nonlinear amplifier in the sense that it produce a response something like that. So, the basic idea of using this nonlinearity is that signal sample values which are going to occur with lower probability, right, which are typically going to be the higher values of x or higher values of x, they will be compressed into regions which are smaller, right. So, let us say this region gets compressed into this region, right, whereas the corresponding region here for the same interval would be only this much, right. So, if I go to the next value, it is going to be still here, because x has much smaller probability of lying in this interval, right. I compress this entire interval into a much smaller interval, and in this domain I do uniform quantization. Now I give equal importance to all the values of y that I get. Okay, it's effectively doing the same thing in a different way. A larger region, a larger interval of x is compressed into a smaller interval in terms of y, but having got this having done this compression, I treat y with uniform quantization, right. So, this is what we mean by sample compression. This is the sample compression I am doing, followed by uniform quantization, right. And at the receiver, of course, your signal value will get distorted now. You are not transmitting the actual signal value, you are transmitting some alternative value.
But that is only another dimension to the signal.
Sorry?
It's only another dimension to the signal. What are you doing? And looking to the y-axis.
No, but this is what I am finally transmitting. But I am not transmitting this value. I am transmitting some value which lies in this interval. So, instead of transmitting this value, I am transmitting this value, and there is a nonlinear relationship.
And in my output, I will be getting y values.
Right. So, I must convert them back into x values. So, what should I do at the receiver? I should do an inverse operation to this, right. So, I have a compressor of this kind, at the compressing amplifier at the transmitter. At the receiver, you have an inverse characteristic, an amplifier with an inverse characteristics, which we call the expander, right. So, we carry out a compression of the transmission and expansion of the receiver, and for various reasons this operation of compressing and expanding is typically talked about together and is called companding, right. It is a short form for compressor plus expander, right. So, this companding is a very common practice used in PCM, pulse code modulation, to effectively utilize your number of bits that you allocate in a much better way, right. There are two commonly used compression laws in the industry. One is called the mu law compression. Now, these laws look very complicated, but they are fairly easy to implement, and they have been arrived at through a lot of empirical research, right. And the other is called A law compression. These are industry standards. One is an industry standard European, based on European standardization process. The other is based on the American standardization process, and this is what they look like. Do not ask me too many questions on this, because one, we do not have time for it, but I will just give the expressions just for the sake of completeness. These basically specify the nonlinear characteristics of the amplifier that you need to have at the compressor. That is all. So, this is a mu law compressor, right. Basically a log compression, the logarithmic relationship is some kind of a compression relationship, is based on that, right, and typical value of the parameter mu is taken to be about 100, right, and the A law is similarly given by more complicated expression. I am doing this just for the sake of completeness. Let us not worry too much about where these expressions come from. and here A is typically taken again to be of the order of 100, right. Anyway, both are some kind of logarithmic compressions, right, arrived at independently by different people. The important feature of these compression characteristics is these are largely independent of the distribution function that the signal might have. Incidentally, suppose I ask you the question that I have some distribution of x around in terms of x, but I want to carry out a transformation of y equal to g of x such that y has a uniform distribution. What kind of function will do the job? Do you know that? Y is equal to? If you choose this mapping function, this will convert y into a uniformly distributed random variable. So ideally I should choose this compression characteristics based on the distribution function of x. What these ALA and MULA do is they make it more or less independent of this, right. They are fairly robust to distribution function. They don't, of course there will be some variation, it will not be really optimal, but they come pretty close to the optimal for most of the kind of distributions that you see in various kind of signals that you use, speech and music and things like that. All right. Now, one final thing before I finish with my PCM, I have discussed the transmitter. A few things that you should know about the receiver. Right? I have not discussed anything about the receiver. What should you have at the receiver? What does your receiver look like? Right? Before you talk about anything else, please remember that there is already one complication that we have introduced for the receiver. We are transmitting groups of bits to represent one sample, right? And these groups of bits are following one another, right? And now I have an additional problem which I never had in any analog system, even in pulse amplitude systems pulse modulation systems that I discussed so far. Namely, I must know which group of bits represents which sample, right? I must have synchronization, right? I must know precisely, here is a continuous set of bits coming along, but whether it is these 3 bits which represent the sample or these 3 bits which represent the sample has to be specified, right? So you need to have you need to introduce some way to tell the receiver how framing has been done, right? So that introduces a very important problem of synchronizing at the bit level as well as at the block level, right? You must know precisely the time instance at which bit levels might change, and also how the bits are grouped, which 7 bits represent the sample, which group of 7 bits, and of course once you establish that once, then there is no problem, right? So one additional complication is that of synchronization. Now let us say we have sorted that out. We are not going to discussion of that. You will learn more about all these things in a course in digital communications if you decide to take it. But suppose you are carrying this problem, you are taking care of this problem. There is an additional problem. This no matter what you do, there will be noise coming along with this. What you will really get is not these clean samples that I have drawn here, but noisy versions of this. And what is the job you have to do at the receiver now? Before you can do the decoding and things like that, you have to simply be able to carry out the job of saying whether in a particular interval the signal that you have seen is a pulse of amplitude some value 5 volts or pulse of amplitude 0. It's a positive pulse or 0 pulse. It's not going to be 5 volts. It will be probably 5 microvolts or 50 microvolts along with noise, right? Was it supposed to be 1 level or a 0 level, right? How do you decide that? No, you can't do a straightforward quantization because a noise spike can easily make you take a wrong decision, right? So somehow you have to have a filter at the receiver which will average out the noise first, remove the effect of noise within the pulse, right? And then only you take a decision whether it is 1 or 0. So this is a very important subject by itself. The decision making process, which looks so trivial, actually is a full-fledged subject by itself in communication theory. We call it detection theory, right? The subject of detection theory. And one of the simplest results is you use a filter at the front end which is called a match filter. right, which will remove the noise. Follow this match filter output by a D2A converter, right. Follow this by low pass filter, because now the match filter output will give you these groups of bits. These groups of bits will convert, the D2A converter will convert these groups of bits into a sample value. These sample values are represent the signal in the pulse amplitude modulated form. Pass that through a low pass filter and you are able to recover your message signal empty. So you require to do all this plus synchronization. That is your PCM receiver. So that's in a very short form an overview of pulse code modulation, which I normally do in 2 lectures, but I do not know, I have done it only for, we didn't have time, but I think I have still told you most of the things. What we have missed out on for both delta modulation and to some extent on pulse code modulation, not too much in pulse code modulation, is the quantization noise performance. For PCM I have done the quantization noise performance, at least for the simple case of uniform quantization, right. But for delta modulation it is left as a self reading exercise. Thank you very much.